A very good morning to all. Today is Environment Day, and we should come up with some dedication to purify our environment. And the first part is air. Then we'll go beyond this air is water and this greenery, other things. Today the topic is air pollution, its health effect, and remedial technology. So I'll first discuss on air pollution, then I'll go towards the health effect side, then we'll discuss about the remediation technologies what are available with us. Any one of you, can you tell what is an air pollutant? Anyone? What is an air pollutant?
Sir,
Okay.
air pollutant are gases like CO2.
Yes. 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 So, first of all, we should know what is pollution. The first term is pollution. So what is pollution basically? So anything what which we are not needing, those are pollutants for us, like this. Suppose I have a wristwatch. Okay, I have a wristwatch, and I am using it for a long time. After certain time, I thought that this is not of use to me, so I'll throw it, and it is becoming a waste to me. But the rag pickers who are collecting those waste, the waste material which is for me is now a resources for those rag pickers. So I cannot say absolutely that watch is a waste. That might be a waste to me, but that is again a resource to a rag picker. जो कबाड़ी वाला जो उसको ले लेते हैं उनके लिए रिसोर्स हो जाता है. ओके. Like similarly, the pollutant, when we are defining the pollutant, that means for whom, what is the concentration level, and what are those things and what are their effects. Based on that, we can say that these are pollutant and these are not pollutant, like this. So the government has defined or fixed some standards. So based on that standards, we can say that if the concentration of that pollutant is beyond that standard, then we can say these are the pollutants. If less than this, then we can say that it is not polluting to the air. Okay. And how we are fixing this standard? To fix the standard, we have to learn about the exposure and the dose response curve. Like what is the dose of that pollutant and what is the response from that. So for that, for example, if anyone can see here my screen, suppose here is dose. Is my screen visible now?
Yes, sir. Yes, sir. It's visible.
Yes, sir, it is visible.
Suppose here is dose. I think there is some problem in this pen. I'll come to that point in the later stage. Let us move from this slide. I'll come to that point. So basically, the presence of any substances that might be a solid or liquid or gas in atmosphere in such a concentration that may tend to be injurious to the humans or animals or plants or property or the atmosphere itself is referred to as air pollution. Okay, so that means first thing is the pollutant may be solid, liquid, or gas. We cannot say that air pollutant means it is always gas. It may be solid like particles or liquids like any kind of aerosols or gas. So the pollutants might be solid, liquid, or gas in atmosphere in such a concentration. This is very important. So beyond this concentration, we'll say these are pollutants. And if the concentration is less than such a concentration, what we are defining here, if the concentration is less than this such a concentration, then we cannot say these are the pollutants. Okay. Again, the third point is to whom. For whom we are defining, like humans, animals, plants, property, atmosphere itself. So the pollutant is poisonous to humans, animals, plants, any kind of property. Suppose Taj Mahal is a property, and if the SOx and NOx are deteriorating the structure, then we can say these SOx and NOx are pollutant for this property. Okay. And the atmosphere itself, because in atmosphere the proportion of these gases are also changing depending on the concentration of pollutants, so it's also poisonous to atmosphere itself. So the pollutants may be solid, liquid, and gas, and there is certain concentration beyond which we can define this as pollutant, and it is harmful to humans, animals, plants, property, and the atmosphere itself. Okay. So from this definition we can clear our concept about the air pollution. Okay. And this pollution problem is three dimensional. Okay. So if something is released to the atmosphere, you cannot control it in the atmosphere easily, because there is no certain boundary to it. Like water, if some stretch of water in the river is polluted, then you can put a dam or some obstruction, collect this water and treat it again. The treated water you can discharge into the river, so that you can do it easily. But for in case of air, once the pollution is released in the atmosphere, it is very difficult to control those pollutants in the atmosphere. So the transport is also beyond our control, and also the impact may be instant or chronic. Suppose sometimes if there is certain high concentration is released in a very short while, that may impact very instantly. And sometimes if the pollution is gradually like pollutant is gradually emitting from stacks or any other sources, and that may have a long term effect, and that may come up with a chronic disease. Okay. And the receptor or medium almost impossible to control those pollutants. The pollutant can control in three stages. At source you can control it. In medium, like in air or water, if the pollutant is moving, you can control that one in medium. And at receptor level, like we are the receptors, or the trees or the buildings or any animals, those are the receptor. So receptor level also we can control those pollutants. Like we can put on mask and pp, personal protective instruments, to protect the pollutants to enter into our body through skin or through nose or through food. Okay. So those are the protection we have. Like we can control the pollutants at the source. Suppose from a chimney some pollutants are released, we can control those pollutants at the chimney or before the chimney. That is the pollution control at source. Or if you can control in the medium, suppose in the air it is moving, if we can plant trees and other things, green belts, so that it can be obstructed, some particulate matter that will collide with the leaf of the plants and that can drop down there. So the pollution can control in the medium. And at the receptor level we can put on mask or any other things such personal protective devices or personal protective medium, which will control those pollutions. Okay. But to control in medium and at receptor is very difficult in case of air pollutants. Okay. And the solution cannot be delayed. We cannot delay. Suppose in Bhopal, what happens in the Bhopal gas tragedy? The MIC, methyl isocyanide, has been released, and it was in at night time. Okay. And within 3 to 4 hours, thousands of people have been affected or dead. Okay. So if you delay by 1 hour, that also matters. So you cannot delay this pollution. So you have to control at any cost. That is the thing. But once the water is polluted, you can delay, you can like collect it. But in case of air, it is not in your hand, so it is very immediate. You have to act upon it, how to control or how to dilute those concentration. Okay. So that is the thing. So in right side you can see there is a curve dose of pollutant. You can see in the x-axis dose of pollutant is there, and in the y-axis the response of the body is there. Suppose how we are defining this dose. Suppose the SOx, suppose I will define the concentration is 40 ppm, suppose. Okay. So on what basis I have defined it? Initially, the scientists have to go for the study, like some mice or some pieces, everything, or the rats. They will like suppose 100 number of mice they have studied. They put those mice in a closed chamber, and they put 40 suppose 60% of 60 ppm of socks inside the chamber. They found that two mice are dead. Okay, so they increase this 60 ppm to 100 ppm of socks inside the chamber. They find 50 mice dead. That means 50% of these mice begin to dead in 60 ppm or 80 ppm, whatever may be. So now they can say that LD50, lethal dose 50, is the 60% or 60 ppm or 80 ppm of socks. If in 60 ppm of socks inside the chamber 50% of that mice die, then we can say the lethal dose of SOX is 60 ppm. LD50 is 60 ppm. So like 50% of the mice die. Similarly, the dose may be defined based on the dose response curve, and you can see the TLV, threshold limit value. Such a concentration what we have defined, that is nothing but the threshold limit value. Up to what concentration we can allow the the pollution to go ahead, and beyond that we should not allow. So that is the threshold level, and it defined the threshold level based on this dose response curve. Suppose we defined that till this level, suppose 100 mice we have tested, so 2 mice are died, so 98 mice are now live. So that means till, suppose we think that till this concentration level we can allow, that means this is the threshold value for us, and based on that threshold value we have to define what should be the permissible value. So the permissible value should be below the threshold value. So that is like we can define this permissible value by dividing the threshold value with some factor of safety. Suppose we take a factor of safety 10, then we can divide this threshold value. Suppose here 60 ppm is socks, so we can divide this 60 by 10, that will be 6 ppm. Then 6 ppm we can say this is the permissible value of socks for in the atmosphere. So based on this we are defining again. So for the mice experiment we have done it. So this concentration is for mice, and the weight of mice is different from the weight of elephant and from the weight of men. So the concentration which we have defined here, it is for mice only, not for men, not for elephant. So based on the weight, if the weight is more, then the concentration dose we have to the standard concentration dose we have to increase, because it will not affect the whatever the 6 ppm of this socks is affecting a mice of 200 gram or 250 gram, whereas the 6 ppm may not affect the man of 70 kg. So the standard of this concentrated socks for men should not be 6 ppm, it should be 60 or 50. That depends on the body weight factor. So the scientists has come up with some concentration which is made as the standard, what we can see here. In the next slide I'll show the standard, how we are making the standards. Just come to this point that from this dose response curve we are getting the standard concentration of those pollutants. Okay, so now if you have any question related this standard and how we are fixing the standard, you can ask me, then we'll go ahead. If anyone has any question related to the standard concentration standard, anyone? Okay. Okay, so I'll go ahead. This concentration standard also depends on the duration over which we are measuring this concentration or considering this concentration. Like suppose we are considering the concentration for 1 hour and for 8 hours. Whether the concentration for 8 hour standard is same as for 1 hour or not, that we have to check. In the left side the figure is the ozone concentration in ppm. Sorry, there is certain mistake here during ri, during exercise. Okay, so some person that black dots or blue dots are the persons whose force expiratory volume in 1 second is actually given, and the pink ones are the persons who are at rest, and the blue ones are the persons who are doing exercise. So you can see the concentration of ozon. What is the highest concentration of ozon here? 0.5, around 0.5. Okay, sorry. The highest concentration here is 0.5. Okay, so zero point 0.5 concentration is you can see it, the pink one is at rest. So whoever is at rest, they are facing more trouble, or whoever are like doing some exercise, they are facing more trouble. Can you choose here? When the concentration is 5 here, when the concentration is 5 here, the concentration is at related to 0 or something here. So you can see when the concentration is around 0.5, at this stage, the people who are not doing any work, they are safe. But however, the people who are doing exercise, they are not safe in this concentration level. So that means whoever is doing some work, their lungs are like exercising something, and their lungs are dynamic. So the concentration for them, we should consider the concentration for them should be less, and the persons who are staying like stable, who are not working, the concentration for them is little more. Like during the preparation of standard, the stable persons should be permissible to a higher concentration level, and the people who are underworking, they should be permissible to a lesser concentration level during the preparation of standard. So when we are preparing the standard, you can see here 1 hour standard, then 1 by 10 into x 0.5, that is the concentration 0.5. Then 2 is the safety factor we are taking here, and this 0.030 is the baseline concentration. What is the baseline concentration? Suppose in the atmosphere now, the SOx, SOx, we are preparing a standard for SOx. So in the atmosphere, the SOx is 40 ppm, suppose. Okay, so we are preparing a standard concentration for SOx. So considering the baseline, we have to go ahead. Suppose we are preparing a standard, so after 40, we know throughout the atmosphere, everywhere, if you measure the SOx concentration, it is 40. You cannot come a concentration which is below 40. That means the atmospheric standard concentration is now 40 ppm. It is the baseline. Then you can permit 45 or 43 or 46, whatever that is beyond 40, that is 6 ppm. You can say that if you are permitting 46, then you can see 6 ppm is the permissible, then 46 is the standard, 40 is the baseline. Baseline means of that area. Suppose you will go to western countries, their baseline concentration is something else, and in eastern country, our concentration baseline concentration is something else. It depends on the temperature and climatic factors. So based on that, the baseline concentration is different. So based on that baseline concentration, we have to fix the standard, and based on the standard, we can say this is a pollutant and this is not a pollutant. If the concentration is beyond that standard, we can say it's a pollutant. If it is not that, then we can say it's not pollutant. Simple. So from this, we can easily find which one is a pollutant and which one is not a pollutant. Okay. So here, ozone, for the example of ozone, I can say the standard concentration for 1 hour, I am considering the highest concentration. But when where I am preparing a standard for 8 hour, so I am considering the lowest concentration. You can see here the lowest concentration is considered 0.04 ppm, like the lowest concentration here. So when I will consider a standard for a longer duration, I have to consider the lowest concentration, okay, in the atmosphere of that particular pollutant. And when I will consider for a very shorter duration, suppose I will prepare a standard for 1 hour, I'll say that for within 1 hour, if some pollutant is released beyond this concentration for 1 hour, then I'll say that this pollutant is having hazardous effect. So for the standard of 1 hour, I have to take the highest value of that concentration, and for the standard of lowest, the long duration, I'll say the lower concentration of that standard, that particular pollutant may be considered. So these are certain things which we should consider during the standard preparation of standard. Based on that, let's come to this side. So here we have to think many things, like some are the sources. Suppose here these industry are the sources, and these are the sources. Once sources is there, then here these sources are coming, the pollutant are coming to the receptor, maybe the plant or human or anything, and this is the medium. Okay, so we have to measure the concentration here, or monitor it. Then we can find what is the concentration, or we can predict what is the concentration which will reach the receptor or human. Or another thing, we can model it. We know the concentration here at the source, and we know the distance of these humans or xyz coordinator of those receptors. Then we know the other parameters like the wind velocity, temperature, everything. Based on that, we can model if some x amount of concentration is released here, the pollutant is released here, then what should be the concentration of this particular pollutant here at the receptor, based on the modeling. Okay, and so suppose here is the pollutant x1, I can say that this x1 is either dangerous to man or not. Okay, based on the standard of that pollutant, whatever is defined. Okay, suppose x1 is dangerous, then I have to control this. So what I have to do, I have to control at source, or I have to have some mechanism to stop the pollution in the medium, or I can control it by putting some mask in my nose or something else. Okay, this is the receptor, remediation, or this is the source, this is the medium remediation, or this is the source remediation. So in the source, what we are doing, we are changing the process, like what are the process inside the plant. If we will change the process, then the pollutant may change, or we can put some control device, so that will control the pollutants. Okay, suppose the cost of the control device is more than the cost what we are having. Suppose we are having the mm, uh, uh, demerit of those things to humans or plants, and we assess those demerit in cost, in money, or in terms of money. Suppose it is 100 rupees. Now the cost of the technology is 1000. So it is not wise to like introduce this kind of technology to protect 100 rupees, or to save 100 rupees we have to spend 1000. So that will come with the cost benefit analysis. So what is the benefit we are getting? Suppose here whatever the demerit we are getting by this emission, and what if we are reducing this emission, what is the cost of that technology? If the cost of the technology is much more, then we should not introduce those technology. That is not feasible. Simple. So now coming to this concentration, what we are measuring, nowadays you can see there are so many devices, like some are the sensor based devices, some are the optical measurements, like light rays, everything you might have heard. So if the sensor based devices are there, they are very susceptible to change, like their characteristic, because those are either photochemical sensors, or magnetochemical sensors, or so many things. So those are very susceptible to change their accuracy and their efficiency. So how accurate we have measured that concentration, we have to look into it. Suppose sometimes we have read the newspaper that concentration is Delhi is much more than the concentration in USA, and they are highlighting it in universe or in world that yes, Delhi is emitting more pollutant than USA. That is not true actually, because whatever measurement we have done, we have to check whether our measurement is accurate or not, whether our measurement is like precision or not. Here the example, here in this case it is precise, all the dots are in the same, but it is not accurate, it is not targeted to the center. Here in this case it is neither precise nor accurate. In this case it is accurate but not precise, accurate. All are like target, hitting the target, but not precise. In this case, all are hitting the target and all are at the same point, near to the same point. That is precise and accurate. So whatever we are measuring, that instrument should give us the precise and accurate measurement. Then only we can say, we can believe that concentration, whatever the instrument is giving to us, and based on that we can prepare our plan whether we have to control those pollutants or not. Okay, if the instrument is giving us a very erroneous result, we cannot decide our technology or management things based on that erroneous result. Okay, that will be a very logically inaccurate kind of things. Okay, so here if you look into the standards, there are certain standards for sensitive area, so a certain standard for industrial area, and also certain standards for residential area. You can see here the sulfur dioxide. Okay, it is in microgram per meter cube, 15 microgram per meter cube if you are taking annual average. If you are taking 24 average, the concentration should be more. For certain time we are considering more concentration, so it is 30 microgram per meter cube. And it is for sensitive area like schools, or like the public places, or like the reserve area, or any such reserve forest. And for industrial area it is 80, the annual average is 80. And you can see for residential it is 60. So the standard for the certain pollutant is different as per the location, as for the receptor, and as for the duration. If it is long duration it is less, if it is a shorter duration it is high. And location also, if it is industrial area it is different, if it is residential area it is different. If and also different for the sensitiveness of that things. Okay, so there are so many standards. All standard has been divided here based on the duration and other things. Now coming to us pollutants. So what are the pollutants? Like we know the pollutants may be maybe liquid, maybe gas. Okay, so suppose it is a solid. Solid means what? Anyone? Solid pollutant means it is anyone? Anyone can answer. Solid pollutant means it is basically
So
a
which
particle.
cannot move, so which cannot
No,
move
sir.
on its own from one place to another.
Solid means it is 3D, three dimension.
Yes.
It is a particle. Suppose in the air, what we are expecting? This is particles. We cannot expect in air the boulders or other things. It will not float. It has certain specific gravity. It will settle. Okay. So in the air pollution strategy, we can say solid means particles. Okay, which is 3D, three dimensions. So when we are talking about suppose 30 micron, 30 micrometer. So whether it is a dia or what is it? What is the 30 micron? Suppose I'll say a particle is 30 micrometer. So what you will assume? The dia of particle is 30, or length is 30, or width is 30, or what you will assume? Anyone? Because always the particles are not spherical. Some particle will very irregular shape, some are flaky, some are, because those particles are of various dimensions. So how will know the particle is 30 micron? So whether I will measure this diagonal length or this length, what is the 30? If I'll measure the 30 micron, if I'll say that 30 micron is the particle size, so what is it? 30 micron is dia or what is it? So when I am talking about 30 micron means the aerodynamic diameter of that particle is 30 micron. What is aerodynamic diameter? Aerodynamic diameter is the diameter of a sphere whose density is 1 gram per centimeter cube. That is the density of water, and which settles or falls in a still air at same velocity as the particle in question. Okay, suppose some particle of iron is here, and I have the standard particle here, who sphere here, which is falling only due to specific gravity. Nothing force is over it, only due to the specific gravity it is falling, and the density is 1 gram per centimeter cube is the density of this particle. Whatever the velocity it is reaching, if this particle is falling in the same velocity, I can say the diameter of this particle is 30. Suppose here this diameter of this sphere is 30 micron, I can say this diameter of this particle is 30 micron. 30 micron. Whether this particle is very small or very large, I am not thinking about that size. I am thinking about the velocity. If both the velocity are same, I can say that the diameter of this particle is 30. Okay, 30 micron. So it is a relative, very relative term. So when I'm talking about 30 micron is not the dia of that particle. It is dia of the standard particle whose density is 1 gram per cm cube. That is a spherical particle having the free fall with the same velocity what this particle is falling. This particle might be of very irregular shape, but I'm not talking about the irregular shape or size of this particle. I'm just comparing with some standard particle. Okay, so when I'm talking about 10 micrometer, suppose, that means this is the particle which is falling as the same velocity of that particle which is having the 10 micrometer diameter of sphere, having the density of 1 gram per cm cube. Whatever the velocity of that particle is same to the velocity of the particle which we are talking about. So that is the 10 micrometer. Suppose I am talking about 1 micrometer particle. So that means the dia of the particle, if it is standard particle is 1 micrometer and density is 1 gram per cm cube, it is falling in the free fall with velocity v, and the dia is 1 micrometer, and the particle of our question is falling in the same velocity, so we can assume that the dia of this particle is 1 micrometer. That means the particle, when we are talking about the particle of 1 micrometer in the atmosphere, that means it is not exactly the dia of the particle, it is the aerodynamic diameter of that particle. You should assure, and you should conclude that whenever we are talking any particle size in the atmosphere of 1 pm, 1 micrometer, 2 micrometer, 3 micrometer, that is not the dia of the particle, those are the aerodynamic diameter of those particles. Okay, not the exact diameter of the particle. Okay, because the particle are of various sizes, you cannot define the diameter of those particles. Anyone have any doubt till this? Okay, fine. Then come to the second step. So if the size, why we are concerning about the particle of various sizes, come to this thing, why we are concerning about the particle of various sizes? Because our we have some respiratory system, we are inhaling some air and exhaling something, and we have some respiratory tract. Here you can see, here there is stage 1, stage 2, stage 3, stage 4, stage 5, and our respiratory tracts are there. Some particles may trapped here by the nasal hair, some may trapped here, and some may trapped here. Some can enter into this interior parts. Okay, so based on that, we will suffer various diseases. Suppose some particle trapped here, it can be removed by sneezing. Some particles trapped here, we can swallow it and it can go to the stomach. Some particles are stacked here, there is certain mechanism of our body which can pull these particles off, and again you can swallow it, it can come to the stomach. But if some particles are in this alveolar region, then it is very difficult to remove those particles from the alveolar region. Okay, so the particles which are trapped here, that are basically bigger size, which can enter into this area that is little smaller than this. Then whatever the particle are entering to the interior region of alveolar, those are very smallest particles. We can say those are the particle of 1 micron or less. Okay, so that's why we are talking about particles. So many times you can come across the word PM 2.5, PM 10. Okay, so why you are like considering PM 10, PM 2.5, PM 1? Why you are not bothering about PM 1.5, PM 2, PM 2, PM 3, PM 4, then PM 7? Why we are not talking about that? Why we are talking about PM 2.5, PM 5, and PM 10, PM 1? Basically, when we are talking about PM 2.5, PM 10, PM 1. Okay, PM 10 means the particulate matter less than 10 micrometer, less than equal to 10 micrometer. That means if a particle size is 1 micron, that is also coming under PM 10. If it is 9 micron, that is also coming under PM 10. It is particle matter range which is less than equal to 10 micron, okay, PM10. And PM 2.5 means particle range which is less than equal to 2.5 micron. And PM1 means particle range which is less than equal to 1 micron. So why we have defined these particles in various ranges? Why we are studying? Like PM10 means if the particle is more than 10 micron, it cannot enter into our nasal cavity. Okay, so it is called as respirable. It is called as the particles which we cannot respire. Okay, and if we are talking about PM 2.5, that means the particles which can enter to a certain depth and which can be removed through our respiratory system or tract. Okay, so what are the removal mechanism? I'll talk to you in the next slide. But we can remove it through our respiratory mechanism. Okay, the 2.5. And if it is less than 2.5, that means those particles can enter into the very anterior parts of our lungs, and removing of those particles is a little difficult for us or for our body, and the self removal mechanism of our body will not act. Okay, so for that reason we are talking about PM 2.5, PM1, and PM10. PM1 means it is very dangerous for us, particulate very small particle size, and if it insert into the alveolar region, there is no way to come it out. Okay, so that part of that alveolar will be blocked. Okay, and here at the figure in the right side you can see what are the sources of those particles, and from various sources what are the size of the particles. Suppose I think some part of this slide is blocked here. Here the size range has been given in the bottom. I think it has not come. So the ultra fine particles, that is basically PM1 and less. Fine particles means PM1 to 2.5, and larger particle means more than 2.5 to 10. Okay, fine, then these are the ultra fine, less than 1 to 2.5 and 2.5, like this. So like fly ash, the particle size is here. Pollens, there are certain particle size. Like tobacco smoke, you will get certain particle size range, like this. So it has already been studied, and that has been represented here. So what happens to us when we are inhaling some particles into our lungs? That means some part of our lungs is blocked. The alveolar region. In the alveolar region, what exactly we have, like we have the bronchites and we have alveolars. Like when we are inhaling something, our oxygen is like filled in this alveolar things. If particle is blocked here, then the oxygen carrying capacity of this alveolar will be reduced. That if the particle will like accumulate here, then total alveolar will be blocked, so oxygen cannot enter. So whatever the blood vessels side to that alveol, it will not get oxygen from this alveol. Okay, and it cannot like give the CO2 to this alveol, and it cannot get oxygen from it also. That means this total alveolar part is damaged, so due to the accumulation of particle. So if oxygen is not, our body is not getting oxygen, then what we are like feeling, we are feeling breathlessness, we are feeling headache or dizziness or irritability or nausea, vomiting or mental fatigue, or there are some other diseases also. Sometimes due to choke of lungs we can have death situation. So this is the lung function test. This is giving basically the total capacity of our lungs. Like in case of male, it is 600,000 ml. In case of female, it is around 4,300 ml, around the total lung capacity. And when in normal condition, when we are inhaling, this is the tidal volume what we are inhaling. But if you are like forced to inhale or exhale, then this is the total maximum amount you can inhale and maximum amount you can exhale from your body. And this is the tidal, is this is normal at normal time when we are taking the breath, and this is the inhale and exhale rates. Okay, so based on this curve, this is the total inhale and forced exhale. Based on this curve, we can, if this person is kink like this, then we can say this person is having some problem, respiratory problem. Otherwise we can say it's okay. Okay, so there are certain indication from this graph we can easily measure, and this is being tested through the lungs function test through spirometer. Okay. Okay. So, what is the mechanism in our body which protects us from these particles? We have two types of mechanism. One is actually one is macrophages, and another is mucociliary elevator. These are two mechanisms of our lungs which can help us to remove those particles. The macrophages are phages which are being created in the alveolar blocks, which can neutralize those particles, very fine particles which are entering into our alveolar. But what is the ciliary, mucociliary mechanism? Suppose this is the thoracic region, and from which you have two bronchites. Okay, and in this region, if we'll see the inner structure, there are certain cilia means air like structure, and there are certain mucus like things is generated by our body and these cells. And this mucus, when particles try to enter, this mucus are like saliva like things. They will the particles will stick to those mucus, and agglomeration of particles occurs. And we have certain upward flow of these hairs, those hairs which are moving, which are like healing upward, those hairs which are healing upwards, always which are healing upwards, that those hairs will pull this mucus or this blocked particle to off. When particles come together and blocking here due to the mucus, this cilia will pull it up, and again it come to the throat, and we can swallow it. It can come to the stomach. Okay, and that can be easily digested and removed. So those mechanism is called mucociliary elevator. Why elevator? Because it is against the gravitational force. When the particles come down, it is the gravitational force through which it is coming down, but it is against the gravitational force. That is elevator. And mucocilia, because the mucus and cilia is acting, that's why this mechanism is called mucociliary uh, elevator. And it is works for the bigger size particles. When the bigger size particles comes, and like 2.5 micron particles comes, you can say it can easily 2.5 to 1 micron, it can easily be traced here, and it can be removed through this mechanism. Okay, and if the particle is less than 1 micron, if it is entering in this alveolar region, then macrophages are the things which can neutralize those particles here. But the generation of macrophages in our body is limited. Suppose in 1 minute 100 macrophages are generating. So if in 1 minute you are getting more than 100 particles which are less than 1 micron size, then the macrophages cannot control the particles. They can control up to 100, because 100 macrophages can control 100 particles. And if the particles are more than 100, you are inhaling in 1 minute, and the macrophages generating is 100 in 1 minute, then the more the particles, suppose 150 particles you are inhaling in 1 minute, and in 1 minute 100 macrophages are there, then 50 particles are there which the macrophages cannot neutralize. Those 50 particles will accumulate in your alveolar region, and that will block the oxygen passage. Okay, so these are the two mechanisms which are there in our body, self removal mechanism of our body. One is macrophages, and another is mucociliary elevator. Okay, now coming to this health, what are the health problems we can have, like COPD or asthma or pneumonia or lung cancer, tuberculosis, or genetically induced any kind of diseases. Okay, and like what are the particles, like fine particle matter can have respiratory system problem, or carbon monoxide. You know, the carbon monoxide, if it enters into our body, what happens to our body if we are inhaling carbon monoxide? Anyone, what happens to our body if we are inhaling carbon monoxide? Our blood cell is hemoglobin, is it? Hemoglobin is there in our blood, and the carbon monoxide can easily replace these things. And the whatever the in the hemoglobin, whatever the parts are there where the oxygen is being trapped, the carbon monoxide will remove those things, these oxygen trapping things. It will just stick to this, so oxygen cannot be trapped or stick to the hemoglobin. So we are not getting sufficient oxygen. So this disease, there are some disease we are suffering due to this carbon monoxide, this methanohemoglobin. So that is the disease we what we are suffering due to the carbon monoxide. And you can see the oxygen of nitrogen and also sulfur, that uh, also affects our lungs. And there are, apart from this SOx and NOx, there are other hazardous pollutants which can also affect our respiratory system, that are the lead and other things. Now, just conclude what we have learned till then. Then we'll discuss about the mechanism of removal and the attenuation process. So till now we have studied that there are certain standards. Beyond those standard of pollutants, if the concentration of that certain pollutant crosses are the pollution or pollutants, and the standards are prepared based on the averaging time, allowable accidents, method of measurement, then local air quality, that is the baseline concentration, then economic of the local area, then precursor level, everything we have to consider. Based on that, we can say that this is the standard, and based on that standard, we can say this
मैंने
particular.
सोचा DOS खत्म है।
Yes.
आपका वो ये उधर का हो गया इलेक्ट्रॉनिक्स का। इलेक्ट्रॉनिक्स उन्होंने 30th को कंप्लीट कर दिया, मई 30th को ही। हाँ वो सब चले गए थे ना फिर। हाँ
So, ma'am,
इनके आउट ऑफ स्टेशन की वजह से।
okay,
Sorry, sir. Please continue.
मैम कर
okay,
दिया।
okay.
I request the
So,
participant please mute your mics and attend the lecture. Yes, sir.
okay. So these are the standards, and based on that standard, we can say that this particular thing is a pollutant or not. If it is beyond the standard, we can say this is a pollutant, or if it is less than that, we cannot say those are the pollutants. Okay. Now, how we are predicting those pollutants? Suppose in certain leakage, we think some M1 mass is leaked. How will predict at the receptor? At the receptor this much concentration is reaching, how will predict this? Due to the it is through certain model. Okay. So this pollution is basically here in this case, suppose there is a certain vessel, certain leakage is there. Okay. Then this pollution will released continuously, is it? In the vessel is totally filled up with some pollutants or gas, and certain leakage is there, the gas is continuously emitting. Okay. And this is called dispersion from a smokestack or certain if it is a sudden leakage, then also this kind of things will happen. Suppose there is a puff means cigarette puff, you can see sudden some pollutant release and it stops. Then this whatever the pollutants released or gas released, that will try to disperse in the atmosphere. Okay. In certain distance or certain time. Okay. So that is the pop kind of things. It is not continuously releasing, it is releasing at certain interval. Okay. So in our chimney, whatever the pollution we are getting, that is due to the fluctuation and turbulence. There is constantly change in the AD diffusivity, and the traditional transport phenomenon equation will not be accurate for predicting the dispersion. The solution is to assume that the material spread out in a normal Gaussian type distribution. So that is our assumption, that the material is uh, s- like dispersed in a Gaussian distribution pattern. Okay. Suppose here is certain emission, and over time and distance, you can see this emission is spreading. Okay. So if you are sitting here at about 7 a.m., you sit here, you think the concentration is this much. Okay. And if you will sit here 7 a.m. to 9 a.m., suppose during this 2 hour, if you will measure every point, like in 7 a.m., the concentration is this much. After 7.5 a.m., the concentration you will measure. You accumulate those concentration, or sum those concentration from 7 a.m. to 9 a.m. The concentration, total concentration at this particular place during this 2 hour is much more than the instantaneous concentration what you are getting here at a particular time. Suppose at 7 a.m. you are getting 5 ppm, suppose, and during the 7 to 9, if you will sum, you will get 500 ppm total. So whatever the total ppm you are getting in the particular place during this 2 hour, and it is much more than the instantaneous concentration what you are getting here at 5 p.m. Okay, that is 5 ppm. Okay, that means the instantaneous concentration is less than the total concentration. Okay, again the spreading is like in Gaussian pattern. It spreads in both direction at a certain time interval like this in x-axis, also in z-axis. So considering those things, we can have a Gaussian plume distribution. Suppose here it is a chimney. Okay, it is a chimney, and the chimney has a height h, and this is plume rise. This side is called plume rise. This side is called plume. Why plume rise? Because inside the chimney the temperature is different. Okay, when it's the gases comes out, then the temperature is the atmospheric temperature and pressure is atmospheric pressure. So whatever the plumes release, that will sudden go up, until it will go up till the pressure and temperature to be same with the atmosphere, then only it starts spreading. Okay, it starts spreading. So that height till which it will not spread, that height is called the escape velocity, the escape height. And that we can say that this is the small this is small h is the chimney height, and the escape considering the escape velocity and escape height and this chimney height, we can say the total height, gross height, is capital H. Okay, and beyond capital H the plume starts spreading. Okay, and the plume starts spreading in which direction? In the wind direction, where the wind will act. So in this case our assumption is the plume starts spreading in y as well as in z direction. Okay, in y as well as in z direction. And in x direction we are not considering the plume to be moving, because we are assuming that in the x direction the plume is moving without any dispersion. Okay, because the velocity of wind is much more than the dispersion, that we are assuming that the plume is not spreading in x direction, because the velocity of wind is much more than the dispersion. Okay, so based on that we can consider calculate the concentration at the receptor. Suppose there are certain wind velocities. Suppose the wind speed is less than 2 meter per second, and it is in daytime, strong wind is there, then I can say the stability class is A. Based on that stability class we can say that sigma y is this much. What is sigma y, I'll tell you. And based on this sigma the stability class also, we can define the sigma z. Suppose A, we can define the sigma dash z, and this is the distance from, suppose here is the chimney, and this distance is suppose 200 meter, and the stability class we got is A. So beyond 200 meter in x direction we can say this is in this range 102. The sigma z will be 0.087 x to the power 1.10. So I'll get the sigma z. What is sigma z and sigma y? Like suppose a plume is released here, in the y direction it is spreading like this. So from this to this distance I can say this is the sigma y coefficient. If the sigma y is more, then it will spread more in this direction and in this direction, and if the sigma z is more, then it will spread much more in this direction and in this direction, like this. Okay, so sigma z, it depends on the sigma z and sigma y. That's why we are considering the sigma y and sigma z here, and we are not considering sigma s, because we are considering in the x direction the wind is blowing in so fast that it is much more than the spreading of the pollutant in that direction. पॉल्यूटेंट उस डायरेक्शन में ज्यादा स्प्रेड नहीं हो पा रहा है जितना स्पीड से विंड ब्लो कर रहा है उसको खींच के ले रहा है. इट इज एडवेक्शन नॉट डिस्पर्शन. ओके, नाउ we can have this equation, the concentration at any point xyz. Suppose here the chimney is here. Okay, and I want to know the concentration here. I know the concentration here C1. I want to know the concentration C2 here at a distance of suppose 200 meter and downstream, and from the center, and in this distance y is suppose 100 meter, in this direction, in this point I want to know the concentration. So how will know? So we know the wind is flowing in this direction. This is u. So based on that, I can say the QM is the thing which are mass of the pollutant which is related in the released at the chimney, and sigma y, sigma z we will get from that table, and U is the velocity of wind. U is the velocity of wind at this chimney height where it is spreading. If you know the velocity here, you can convert this velocity to the chimney height. There is certain equation through which you can convert. Power law is there. Through power law, you can convert the velocity of wind to any height. If you know the velocity of wind of certain height, you can convert it to any height through the power law. Okay. Then you should know the constant the velocity of wind here, that is the U, and the sigma y, sigma z, that is the coefficient of dispersion, and the y is the distance, this distance, and z is the distance of height from the ground. Okay, from the ground. And second thing is here, whatever. Okay, the x is here, maybe the x is the x is not here in this equation because we are not considering x, but to get the stability condition we need this x. For this 200-meter we can go to this previous table. For the stability condition we need the x. Based on the x we can say this is the equation for this, then we will get the sigma z. Okay. So this this is the equation where you can change the temperature, and also the you can calculate this del H, which is basically whatever the howling height when the plume is released from the chimney. After certain time it starts spreading. So this height you can measure, and this height you can calculate from this equation USD by U. Okay, this is the equation to find out this del H, and this is the small h chimney height, and total thing is capital H, what you are getting. Okay, and this is the equation U by U1 equal to Z by Z1 to the alpha. This is called the power law. So like if you know the wind velocity at this level, suppose you know the wind velocity at ground level, you want to know the wind velocity at the chimney height in this level, what is the wind velocity, then because you know the U1 and you know the Z1 in this, because you have some anemometer, you put it in over your rooftop, you know that height of this anemometer and the velocity what is measured in the anemometer U1, the U1 and the H1 you know. Then you know this H2, you want to convert this velocity to the H2 level, the chimney level. So you know the H2, then you want to find out the U2. So you can use this equation to find this one. Okay, so because you need to know the velocity at the chimney so that you can calculate the stability class. Okay, so this is an example or problem what I have given. You can I'll just share this slide so that you can solve it. Okay. Okay, now coming to this. Oh, so we know monitoring, how to monitor the pollutants, how to measure the pollutants. It should be accurate and precise. And now coming to the reduction technology. So what should be the reduction technology and how we should implement? We should implement the reduction technology at source, or at medium, or at receptor level. Source means where it is emitting, medium means through which it is spreading, and receptor means we are the receptor, and the trees, plants, and animals, those are being affected. Those are the receptors. Okay, so in the source we can control the process. Suppose in an industry some gases are more, so if we will change the process, suppose the raw materials you are inputting and you are getting some reactions and then you are getting some gases. Okay, if you will change the proportion of raw materials and other things, if you are changing those things, processes, you can modify those process, and you can optimize your process to get the pollutants down. So that is the process modification. Okay, and second thing is instrument. So before releasing through chimney or through the output, you can put some instruments which will eliminate those kind of pollutants, whether it is a particle or gases. Okay, so that is the source remediation. Then medium means you can have trees. Suppose here is here some industry is there, it is emitting. So you have 30 now government has decided that every industry should have 30% of its area as green belt area. Okay, so suppose surrounding the boundary, you put some trees, and trees are suppose 9 meter, 6 meter, 3 meter height. If your particles are being uh, collide with the leaves of these plants, and the particle being trapped here, and this is being dropped here. So the periphery beyond this boundary will not be affected through this particulate matter. Okay, that is the fundamental what we are. But the plants should be of high dense, and we can design the green belt, because what kind of plant we have to put, and what height should be the plant should be there, and what is the thickness of leaf, and what should be the width of that green belt, so that effective particles can be removed. Okay, these are the things during the green belt design we have to design those things, and I have those design with me, but I cannot discuss here because it's a very less time. But those we can also design, and based on that we can say that 30 or 40 or 50% of the particle can be trapped through the green belt. Okay, these are the medium remediation, because in the medium we are putting this green belt to remove. Okay, sometimes we can control or blow air in opposite direction. We can put humidity or spray like some water to accumulate those particles, and that can be dropped down. And in the receptor we can put mask or any kind of personal protective instruments or personal protective equipments that can also reduce the pollutants at the receptor level. Now coming to this, basically what we are doing in the medium, it is very difficult. At the receptor level, it is also very difficult. It is easy to control at the source. Okay, that is the thing which is feasible for us. So whatever technology we are using, that is basically at the source remediation. Okay, so in the source we can modify the process. That is a specific thing, because it differs from the industry to industry, because every industry has specific process, and based on that you can modify that process to such an extent. Suppose you have x, y, z are the raw materials you are consuming, and you are getting some product 2x, y plus y, z, like some gases like this. So you change this proportion, and you change the temperature and pressure, everything. You change it, and you get the gas, you measure the gas, and you change it, so you will get some curve like changing versus the gas. So whatever the optimum level you get, so that change you are accepting that this change is the optimized change, and that process you have to adapt to get a very optimized level, and the gas concentration is optimized here. So now you can say this level of the process you have to adapt, and the gases maximum you can control to this level. Okay, now coming to this instrument and device through which you can additionally trap some gases or particles. So there are certain instruments for the particle matter and some instruments for the gases. Okay, for the particle matter we are using this gravity settling chamber or cyclone or electrostatic precipitator. Gravity settling chamber, cyclone or electrostatic precipitator. And for gases we have this scrubber or flare. So now come to one by one. Suppose for the particulate matter, you can see the gravitational force, the mechanism, or centrifugal force are the mechanism, electrostatic forces are the mechanism, filtration technique, then scrubbing or absorption also there. For the gases like volatile organic compounds, NOx, SOx, etc., the condensation is there. Then scrubbing or absorption is there, adsorption is there, incineration is there. Then there are flare process, thermal oxidation, catalytic oxidation. Oh, what are those things? Well, we should know. This is the basic thing. Like gravitational force means, as you know, this gravitational means the particle is settled due to the force of gravity only. That means when the particle is being inserted into a narrow area, then you have to open up the area beyond it. Then the particle is getting more surface area, the velocity comes down and it settles. Whatever the particles, if the specific gravity is much more, then that can settle easily at the bottom, and the clean air is removed in the outlet. Okay, and the particles which can be collected in the hooper, and at certain interval, time interval, we can open up this hooper lid, and this particle can be collected at the bottom. Okay, so that is the gravitational force. But for this gravity chamber, we need very bigger area, and also the bigger particle size can be removed, like 40 millimeter to 60 millimeter, like this kind of particles can be removed easily in the gravitational chamber or gravity chamber. But if the particle size is very less, so it is very difficult to trap in the gravity chamber. Okay, now centrifugal force. Centrifugal means there is some cyclone which have some centrifugal forces, and it will like bombard with the surface of this wall. I will come one by one. Then electrostatic precipitator. Electrostatic precipitator means there are certain device through which we have to pass the air, and the device is having two electrodes, sorry, two poles. One is electrode, one is like positive and charged, and another is negative charge. And if you are passing your air in between this, and if you are giving high voltage, then what happens, the particles are being charged, and those particles are being attracted with if the particle is charged with negative, then that is attracted towards the positive end of that instrument. If it is negatively so positively charged particle, then it will be diverted towards the negative charged plate. And then after certain time, if the plates are being filled or surrounded with a heavy mass of particles, then you can stop the voltage difference or giving the power supply to this system. Then you can vibrate the plates and collect those particles at the hooper, and it can be removed. Then you can pass again the air. So those are the electrostatic forces. Then filtration technique, that means you can filter it through the bag, like bag filters are there. You have certain like bag made up of with some fabrics, and the gases are being flow through these fabrics, and the particles are being trapped in that fabric cloth, and those particles can be removed after certain interval. Okay, that is the filtration. Then scrubbings are also there, absorption and scrubbings. For the gases, you can other hand the gases VOCs are the substances which can be emitted at very low temperature. So the low also atmospheric pressure, in atmospheric pressure it can be released easily, the VOCs. So if you will give very less temperature, what can you do? You can condense those VOCs to liquid state, and that can be collected. Okay, or you can go for the scrubbing or absorption. Suppose sometimes you can use charcoal and other things, those can absorb this air, okay, or gaseous matters. And then after absorption, what you can do, you can just heat it, and you can collect those gases by dissolving it from the absorption. And desorptions are the mechanism through which you can collect those gases if you want to use those gases further. Okay, then incineration. Suppose some gases are in heavy amount, heavy quantity, and you are unable to trap with this mechanism, absorption, desorption, and this is not economic one. In that case, you have to go for the flaring system or incineration system. Suppose for an example, when you are extracting oil from an oil mines, petroleum or something. So basically, those petroleum industries, you can say those mines are basically in sea. Okay, when you are exploring those things in sea surface, when you dig, the moment when you dig into the mining of this oil, when the pipe inserts, what happens? The oil come with very high flow. Okay, because that is in high pressure level. So you have certain devices to control those things, but still there are VOCs which are at very high force that is being emitted. In that case, it is very difficult to control those VOCs. So there are flare towers which will burn those VOCs which are being emitted to the atmosphere. So there is burning system at the top of the flare tower that will burn those gases continuously. Okay, so this hydrocarbon can be burnt there. Okay, that is the incineration kind of things or flare process. And catalytic oxidation. Some catalyst you can use to oxidize this unburned things, or to oxidize these gases. Suppose SOx are there, NOx are there, or CO2, CO are there, then you can oxidize those things through catalysis. Okay, now coming to this PM, what we have discussed earlier, PM10, PM2.5, and these are the wind blown dust or volcanic ash or smoke or pollens. or this may be natural or human made. And the particle can be removed various mechanism like gravity settling or
Your
centrifugal
sound,
action or
sir, there
inertial
is breaking
impaction.
in your sound. Hello,
Hello, hello,
hello,
hello.
Dr.
Am
Indramani.
I getting?
Hello,
Yes, yes. Hello. I'm getting your voice, ma'am. Hello, 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 hello. Am I audible?
Yes, sir.
Okay.
Audible, sir. Maybe ma'am is having an internet connection issue. I think so.
Okay, 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 okay. So there are gravity settling, okay, gravity settling chamber, centrifugal action forces are there, like cyclone. I'll discuss one by one. Then inertial impaction is there, electrostatic attraction, like we have some plates, positive and negative plates, and the particles which are charged with negative that can attract towards the positive plates, and which are charged with positive that can attract towards the negative plates. And when we'll see that the particles are accumulated in all plates, then we can stop the flow of electricity, then we can vibrate those plates and collect those particles. Okay, that is the things in the electrostatic attraction. Then Brownian Mason, other things, those are very complex kind of things. I don't want you to enter in this short while for all those things, but we can discuss these four things: gravity settling, centrifugal action, and other things. Okay, now come to this fluid particle. I'll not okay, direct come to this gravity kind of thing. Okay, here this is a gravity chamber. You can see here when the gas is passes through this is the inlet, and in this chamber, the suppose the pressure is something here and the flow is something here. Now sudden the mouth enlarges and the flow reduces, the particles can drop down and that can be removed through this hooper. Okay, this is one kind of things. And at the outlet you will get cleaner air. Okay, similarly it can be you can arrange it in series. Yes. Okay, you can arrange it in series, like this gravity settling chambers. You can arrange it series so that you can get more and more efficient removal mechanism. Okay, so in series, in the hooper, the particles will be collected, and after certain interval, you can open this valves and you can stop flow here, because if you continue the flow, then this if you open this one and you continue the flow, then the gas can pass through this also. So when you are opening these leads, then you have to stop this flow here, then open these leads and collect these particles, whatever is collected at the hooper. Okay, then the clean air being passed continuously, but it is you can use this kind of things very bigger particles like 40 to 60 diameter. Okay, and you can see the mechanism. Suppose the particle can be trapped, the dp star is the particle size beyond which you are not collecting the particles. These particles are not collected in this super, it is going out. Okay, this particle is going out, but the particle which is less than this dp star, the greater than the dp star, that is being collected here. If more than the dp star, the particle size is more than the dp star, then that can be collected here, here, or here. Okay, if it is more than, if it is less than dp star, then it can remove escape. Okay, so based on that, the length and breadth we can design. Like suppose the dp is here, you can see the dp is 0.333, rho is density of this medium or gas, and rho p is density of particle, of which particle you are targeting. Suppose there are steel particles, there are aluminum particles, dust, other things. So they are the density, their density you can consider, and q is the flow rate, and l and b are the length and breadth of this gravity settling chamber. So based on that, you can design. And suppose you are designing the chamber for dp size, this is the particle size, then you can easily arrest the dp to this level, and the particle size, if it is more, then it is can be arrested. But if it is less than the dp, then you are unable to arrest those particles. So that is the mechanism. So based on that, we can say this height h star, So beyond S star, if any particles comes, then you can easily, you cannot easily like trap it. If it is less than S star, then you can easily trap it. Okay. So similarly, there are certain problems in this gravity chamber. What are the problems? Sometimes you are not getting the for the design purpose, you are not getting the flow rate. You don't know what kind of particles. In such case, you can say that velocity. You can say that whatever the velocity you are assuming here, this velocity q. For this, you can assume this velocity as 10, 3.05 meter per second, and other things. This is a standard thing what you can consider. But for aluminum chips, asbestos, everything, the density is defined here. The medium of particle size is defined. The pickup velocity is defined here. But if it is a mix of all things, then you can assume this velocity is 3.05 meter per second. Okay, for design purpose. Okay. Similarly, cyclone. In cyclone, what happens? Cyclone are maybe of three types. One is top inlet. Here the gas is inlet at the top. Here the gas inlet at the axial inlet. Axis the gas is inlet, and here at the bottom the gas is entering in the bottom. So the inlet is the bottom. Inlet may be at top, maybe at bottom, or at in axial level. Okay. In cyclone, what happens? When particle is being rotated inside the cyclone, and it is being dragged and also stuck to the wall of the cyclone, and it comes at the bottom. Particles can be accumulated at the bottom, and the clean air can go at the top or removed at the top. This is the mechanism through which the particle get an inertial force, and then it will stuck to the wall or collide with the wall and collide with each other also. The bigger particles can drop easily, and the smaller particles can be still there. Okay, these are having three parts. One part like the air is entering in this area, and second part is this one. Third part is this one. Okay, so where the inner surface is gradually reducing, so that particle can be collected easily. Okay, and these are the three parts what we can design also. I'm not going to the design, but the further application I am considering, like we can uh, collide, or we can agglomerate, or we can arrange those cyclones in series or in parallel. Okay, so suppose you arrange two cyclones in series, so what is the demerit and merit? And suppose you arrange two cyclones in parallel, what is the demerit and merit? Series means only the whatever the air is coming from this system, and you are passing through this cyclone, then second cyclone, then it is being emitted in the chimney. Okay, this is in series. And in parallel, what is happening? Whatever coming from the system, you are directly giving it to both the cyclones. So it is being divided in two things and directly giving to both the cyclones. It is not in the series, it is in parallel, both sides. Suppose some cyclone, what is the demerit here you are getting? Suppose some cyclone is more efficient, so it will take more and more air. Some cyclone is very less efficient, so due to some mechanic problem, so it will take less area. Okay, so in this case, there is certain problem, because whatever the efficient cyclone, that will get more load, and sometimes it can stop working. But in case of this series, what will happen? The higher pressure drop will be there, because here will be some pressure drop, and here also some pressure drop you will get. Suppose this two pressure drop will be added, so higher pressure drop will be there, and that is a disadvantage for this series system. But in case of parallel system, what is the disadvantage? Because difference flow rate, sometimes the flow inside this cyclone will be more and this is less, sometimes this is more and this is less, and the flow due to this difference in flow, there will be certain problem in the parts that is minimal, and you can tolerate that one also. Then higher volume of gas can be treated at reasonable pressure depth, very less pressure depth comparing to this series connection. So this is more favorable, the parallel things is more favorable. Okay, so this is the chord diameter. Chord diameter means what are the how you'll decide what kind of particle size you can trap through the cycle. So that is the chord diameter, DPC. Okay, so this DPC you can easily calculate it. Calculate through the n is the effective number of turns, because inside the cyclone there is number of turns. Okay, so that turns you can define n. Okay, that is the n is the number of turns, and the inlet gas velocity VI and other things you can easily learn if you go through the site. then you can find the DPC, what is the core diameter, beyond which the particles can be trapped, and if the particle size is less than this DPC, that cannot be trapped. That is the things. Okay, so here you can easily see the DPC, if the particle size is DPC or less. If it is less, then 50% DP cut is 50% of the particle you can trap. If the particle size up to this, then beyond this particle size, 100% of the particle can be trapped. Okay, and if it is the particle size is this size DP cut, then 50% of the particle can be trapped like this. Okay, so based on that, we can assume we can also calculate the efficiency of this. Now coming to the electrostatic precipitator. The electrostatic precipitator consists of three fundamental steps. One is particle charging, another is particle collection and removal of the collected dust. Okay, so how you are charging the particles? As I have told you, like there are two plates here, suppose, and it is being charged with two supply lines. The voltage difference we are giving like some kV in terms of kV, kilovolt, and now you are passing the air is having some dust and also some gases. Okay, so now what happens when you will give too high voltage difference to these gases, then the gases will be ionized. The gases will be ionized. Ionized means you will get ions. These ions will stick to the particles, and the charge, the particles made some charges, like some positive particles and negative charge particles. And there are certain electrodes and this metallic plates, and the positive are being attracted towards the negative plates, and the negative charge particles are attracted towards the positive part, and the gas will be, the clean gas will be removed. This is little good technology, or in terms of particle removal technology, ESP is very good. But there are certain things like if the sulfur content is more, if the humidity is less, in that case there will be certain problem in such kind of devices. So we have to take care of that. If the sulfur content is more, then in that case we have to spray more water inside it to increase the humidity. Then only because there are certain problems related to the sulfur. So in advanced technology, you can go for that, and that is the optimization thing what you can do. So in electrostatic precipitator, we can really trap very fine particles also. But it is a costlier technology we have. So initially we have to charge the particles, then trap the particles through various plates, negative and positively charged plates, and then remove that things. When we are removing, suppose the plates are being filled with the particles. Suppose the particles are there, they are filled with. Now what happens? The plates cannot more accommodate these particles. It cannot attract the particles more because the particles are there already in the surface. Very thick layer of particles has been accumulated. So in that case, we have to supply the electricity flow. Now what we can vibrate these plates, and what are the particles accumulated over this plate, that can be dropped down, and that can be collected in the hooper at the bottom, and you can remove those things. So that is the mechanism where we can collect those particles which is being trapped in the plates, and then again we can give the power supply, and the continuous process can continue. Okay, so there are certain terms like specific collection area, like how we can increase the efficiency of the electrostatic precipitator, like ratio of collection surface area to the gas flow. Everything we can optimize it through the design process. I have given those things here. You can go through it. I'll share this slide to you. Then coming to this fabric fiber filters. So when you are giving this some fabric kind of things here. Suppose this is fabric filter. Each one is fabric filter unit. So you are supplying the air, dirty air from one side, and other side the clean air is being removed, and whatever the particles that is being trapped in the fabrics. And the fabric has certain capacity. Suppose this is a fabric. Okay, fabric has certain holding capacity beyond which the pressure drop will be more. When the fabric will be filled with these particles, block the all the pores are being blocked with particles, then the pressure drop will be more. In that case, what we can do, we can stop the supply of air, dirty air inside it. Then we have to remove those particles by backwashing. Backwashing means opposite direction. In this direction you have to flow the air, then whatever the particle is trapped inside, that can be removed, and at the bottom or the fabric. So whatever the initially the bottom of the fabric is you can have a what you can say a lock here, then you can remove that lock, and you can flow in the opposite direction, and then those particles can be removed from the fabric, and that can be collected at the bottom. And that is a backwash process through which we can clean the fabric and get the particles at the bottom. Then again we can continue our process. That is the process through which we can remove the particles through the fabric filter. Okay, and the efficiency of fabric filter is also good. These are certain kind of fabric filters in series also. You can see here what are the fabric filters accumulated with particles that can be collected here at the bottom during the process of removal. And these are certain design parameters I have given to, and the type of fabric, all things I have given here. Now coming to the wet scrubber, whatever things we have described, we have discussed, those are the for particles. Like in the electrostatic precipitator, we remove the particles. In fabric filter, we are removing the particles. Then we are in gravity chamber, we are removing particles, and in cyclone, we are also removing particles. Now coming to the gases. What about the gases in the stream? If gases are there, what we can do? We can go for the scrubbing. Scrubbing means spraying of some liquid over the gas. So what happens? Some gas is being eliminated by reacting with the liquid. Same time, also the particles are being removed through the liquid. Also, some particles, those are being accumulated through the water and spraying of water, and that can be removed at the bottom. Also, some gases that can also be dissolved in water and can be removed. Instead of water, we can spray certain chemicals also to track certain gases. Suppose SO2 is there, we can spray what? We can spray the lime based component. Suppose lime water, we can spray lime water to trap the SO2. Okay, that SO2 can react with lime, and we can collect those things in at the bottom, and the clean air can be removed. Okay, that is the things. Instead of liquid, we can spray certain chemicals to trap certain targeted gases. Suppose in our stream NOx is there, we can spray certain chemicals to trap NOx. If in our stream SOx is there, we can spray certain chemicals to trap the SOx. Also, for other gases, we can come up with experiment with some certain chemicals which can trap those gases. That chemicals can spray over that tower. Suppose the gases are passing through this tunnel, so in this tunnel we can have some mechanism which will spray the gases here at the top. Like here you can see these are the nozzles which are spraying the liquids, and from the bottom the gases are being passed. Okay, or sometimes we can pass the gases from the top also, and the liquid can spread from the side walls also. So many mechanisms are there, but at last at the bottom with the liquid, the particles are being removed, and also the gases which can react with those liquids, that can from some precipitation that come up with some like slag like things, or like some slurry like things, that can be removed at the bottom, and the gas can be removed at the top. Clean gas can be removed at the top. This is the mechanism of the scrubber. So there are so many scrubbers, wet scrubbers we are using for particular gases, and this kind of scrubbers we can use just before the chimney. Okay, just before the chimney we can use those things. Sometimes we can use the mist is nothing but the spraying of water in very minute particles of water, very teeny particles of water, we can say these are the mist. And this kind of things also we can use sometime, or steam kind of things we can use to remove those gases or those particles. Okay, mist eliminators are also there. There are certain demerits and merits. Sometimes we can use the venturi scrubber also, which can have both kind of things. Like it can rotate the gas, same time it can spray the water also. The combination of two three things we can use, like in the gravity chamber. Initially you use the gravity chamber. That gravity chamber can be used with the spraying kind of things. Like you can flow the air through the gravity chamber, same time you can spray water from the top, so that the particles can be effectively removed. Smaller particles can also be removed. So that is the combination of technology. As for your requirement, you can change. Like you can combine the gravity chamber with the scrubber. technology. You can combine the cyclone with scrubber technology. That is the combination of things what we can do with optimizing kind of things. Okay. So these are the flare towers. What at the flare tip we can burn those gases. What I have earlier discussed, that when you are exploring some oils or in the mainly petroleum and diesel products, those things when you are exploring from mines, the gases are being released at the top at a high velocity because there is a high pressure in the mining area. So when you dig those things, the gases are being at high pressure and that is being released in the atmosphere. So you cannot release those carbon like hydrocarbons to the atmosphere. That is that you can say these are the global warming gases having the global warming potentials. So those things should be burnt before releasing to the atmosphere, so that has been burned through the flare tires. At the top there will be flare tire that will automatically burn those things, and that can be converted to CO2 and H2O. Okay. Apart from that, there are also other kind of mechanisms through which you can spray things. Here you can see how they are spraying axially, and then the PDC inlet is in this side direction, and this is spraying axially down. Those are the sprayers which are spraying the water from axially top to bottom, and the bottom the collection water is collected, and at the top the vapor or gases are being released. Okay. So once you control everything, suppose you control everything. Now, first thing is you have certain standard. Beyond the standard, whatever the pollution is released, that you are saying that those are the pollutants. Now you have monitored those pollutants. Then you have modeled those things like through Gaussian plume distribution model or any other models. There are so many models are there through which you can model those things. Like you can you know the concentration which is released at the source. Then through the modeling process you can define that the concentration which can reach at the receptor which is at a distance of this in x, y and z coordinate. You can say that the concentration at this particular point will be this much through your modeling approach. Okay. Now what you have done, so you know the concentration of that particular pollutant for the main is this much. Suppose the concentration of SOx is 40 ppm per man, and you see through your modeling that the men who are sitting at that certain place, they are being exposed to 60 ppm. So you have to reduce 20 ppm. So what you have to do, you have to change the concentration at the source. So at the source, what you have to do, you have to go for the scrubbing technology. Because it is gas, you have to go for the scrubbing. In scrubbing, what you are using, you are using lime water to arrest SOx. So you are using the lime water, spraying the lime water. Now you have to design your scrubbing system to control this 20 ppm, additional 20 ppm, because 40 ppm is safe, but 60 ppm is not safe. So your limit is 40. So you are releasing 60. That means 20 ppm you have to control. So for this 20 ppm, you have to design your things. Okay, you can control this SO2 to 40 ppm level, and you can release that 40 ppm. This is one kind of things. Second is, suppose you have certain device, fabricated some device, you want to model it also, how much the efficiency of that device. Suppose this is a chamber where you have put your device here, the inlet concentration is this much, then outlet concentration is this much. Inside your industry, some gases are being emitted here. This is the source. Inside your industry, some gases are being emitted, and in the atmosphere of this industry, the gases are this much concentration C1, and this C1 is being forced to pass through this device, and the outlet you are getting the C out, concentration out. Okay. So now you want to design this C out should be less than 40 ppm, and C in is 60 ppm. Now C out you should design it for less than 40 ppm, like this. So you can put this C out here. You have this C out 40 and C in 60 or 70, whatever your concentration is releasing, and based on that you can calculate. So what is the number of such device, you have to put here inside this industry. So you can put this number of devices to get the C in C out of certain concentration 40 ppm. So the ER is the emission inside the industries. These are the sources of emission. You can put every value and you will get the N that is number of certain devices to set inside this industry to get the safer limit of CO, safer value of CO out, whatever the concentration out is coming out from that industry. That is the thing we can do. So also you can go for the health risk assessment, like whatever we are inhaling, that you can calculate CDI, and what is the reference dose. Reference dose means that is the standard what we have prescribed or government has prescribed for that particular compound, and based on that you can calculate the index. Okay, so this is the chronic daily intake. Chronic daily intake means how much that pollutant we are taking in. Okay,